Okay. Okay, we can go ahead and get started. I can fit this all in anyway. Okay, so you guys are all here to learn about MPI, specifically a type of parallel programming, and then utilizing compilers in an efficient manner. Okay. So I'm Brock Palin. I'm one of the admins at the Center for the Kane Advanced Computing Group. One of the people behind the curtain running Flux. If you send in a support question, I'm generally one of the people that's taking care of that. I'm going to be using a subset. The first half, when I'm talking about MPI, I'm going to use a subset of slides that I use, and normally a full 2-hour course specifically focused on MPI. You can find the whole slide and example codes that go with them in lecture notes on the CAC training website, and they're all available at the bottom of the normal training stuff I use. So all I'm going to cover today is basically what is MPI and kind of an overview of what it is. So MPI stands for Message Passing Interface. It is actually an API for passing data between discrete processes. So this is not a shared environment. This is where you have independent machines or independent processes that need to have some way of facilitating data transfer between themselves. And you don't want to have all the overhead of creating sockets and stuff like that. It exists in bindings for C, C++, and Fortran. And it's what we call distributed memory programming. This powers a lot of the very large high-performance machines out there. They pretty much all rely on MPI because traditional shared memory models don't scale to 100,000 cores, et cetera. It also gives you added flexibility because you can now take a large quantity of low-cost machines and build what we call a cluster, rather than using high-end proprietary hardware to build a very large shared memory system. So the examples here, I need to update these slides. I'm actually going to be using the Intel compilers, and it's going to be done on Flux, but they would also work on the engineering cluster NICs. So here's kind of what MPI looks like. You have these functions that facilitate data transport between what we call ranks. A rank is a number assigned to a core, generally, but you can also do a hybrid model where you can actually combine shared memory parallelism with distributed memory parallelism. So there's just an example just to illustrate kind of what some of these functions do. You have functions like broadcast, which you have a single core that's got some data, and you want to replicate that across all of the CPUs, you'd use a function like broadcast. So instead of having to loop over every single CPU, you can just say broadcast, and it goes everywhere. And so in the background, the MPI library will do optimizations for you for efficient ways of actually transferring data to many CPUs in a quick manner. You can have other examples like gather, which is collect subsets of data and get it all lined up on a single CPU. And there's the traditional sends and receives so that you can just send from one CPU to another, generally used for like a nearest neighbor or something like that. So this is OpenMP on the other hand. This is one of the other common forms of parallel programming you see. This is shared memory parallelism. It's a little bit easy to understand conceptually, but it has some limitations. But this is kind of how the timeline looks there. You have a single shared kind of process you start, and you unroll loops. So you have like a for loop or a do loop, and you say, these iterations are independent from each other. So do them in groups of 4, 5, 6 simultaneously. And so you get these parallel regions, and then you have an implicit barrier at the end. So if I go back to MPI, notice how these lines never actually intersect. Those lines can be on the same multi-core machine, or they can be on 4 independent computers communicating over a network. OpenMP, on the other hand, the shared memory models can't do that. So in the first case, that could be 300 compute nodes. In this case, it'd have to be a 300-core system. I can tell you which one's more expensive by an order of magnitude. The system to support this. So that's why a lot of people like to use MPI. So there's a couple other types of MPI parallel programming out there. There's high-performance Fortran, which is getting more adoption now, but it's still relatively immature. Some of the compiler manufacturers are starting to support it. If you're going to look at using P-threads, normally for scientific programming, it's easier to use OpenMP, which generally is implemented with P-threads underneath. PVM, do not touch PVM. PVM is dead. It's very hard to even get it to build. So don't bother with PVM. Stick to using MPI. CoArray and SHMEM, you can use these things, but they're generally tied to a specific platform, and support's not that great. SHMEM being specifically a Cray thing. So the other thing that MPI does for you, it abstracts the network you're on. So if you were going to write, if you didn't have a library like MPI, probably the most common tool available for you would be your regular network socket. This is what you use when you're like pull up a web page, you make a connection out over the internet with TCP/IP, and you negotiate something and you move some data across it. That has some limitations. So in high performance computing, we actually have a lot of these hybrid exotic networks. So example, traditional Ethernet, commonly used in low-cost clusters. You're looking at 1 gigabit per second and 40 microsecond latency if you get everything all tuned out. On the other hand, inside a single machine, if you do some sophisticated OS-level shared memory passing, you can get like nanosecond type latencies because you're basically going at the speed of the memory bus. You can also find things like these exotic networks like Mircom or QDR InfiniBand. Flux, the college resource, or the university resource, is built completely on top of quad data rate InfiniBand. It's 40 times faster than regular Ethernet and has 1.5 microsecond latency. It also does some other things that gives added performance. But you don't have to worry about these sorts of things when using MPI. It's all abstracted from you. When you start MPI, you have an application written in MPI, you don't have to worry about the underlying network. You just say, send data from 0 to 1, or from N to everybody. You don't have to worry about the network type. It will automatically choose if the cores are inside the same machine, it will use shared memory. If it's between two machines and InfiniBand's available, it will use InfiniBand. If InfiniBand's not available and there's Ethernet, it'll use Ethernet. And you don't have to worry about this. You program in one model, and you can go from an exotic machine, like say the Kraken machine on Exceed, over 100,000 CPUs in that machine. Fancy proprietary C-star network that's built in a 6-dimensional torus. You can write your application there. You can bring it back to something like Flux, a commodity-style cluster. MPI, still work. No code modification required. Just have to recompile for our system. So this is one of the benefits of it. Oh yeah, and your common 6 megabit Comcast connection is 0.006 gigabits per second. That's to kind of put the performance of those networks into comparison. So MPI messages consist of a couple of pieces. There's the address of the data you want to send. This is normally a pointer or the variable name. A data type, and the number of things you want to send. Then you also have something I call a tag. This is to distinguish between two messages coming from the same CPU. And there's something called a communicator. And then, where are we sending the data to? So there's two starter functions, and then I'm going to skip over most of the other functions. But every MPI application must start with MPI init, and that's how the application figures out how it's going to communicate everywhere, and MPI finalize. MPI, normally by default, you write one set of code, and you execute the same set of code on n cores. N can be 2, n can be 10,000. You only have one unique piece of information to distinguish between the cores. And that's determined by calling this MPI com rank. This is where things start getting interesting. You have the same code, and you run it. Each processor gets a different answer for com rank. And it's 0 through n minus 1. And that's how a processor knows kind of which one it is in this parallel computation. So a very simple model for doing something would be, say you've got something that's statistically independent. So you'd just be like farming out work. Say you just have like a queue of work and you're farming it out to multiple CPUs. You would say, I want to send, say you set 0 is going to be master. So whoever calls MPI com rank and gets 0, they're going to execute one set of code, which is send everything to everyone else. If you're not 0, you do something else. So I'm actually going to pull up an example code and actually show you how this kind of looks. Okay, survey says Fortran. Okay, C. Okay. So here's a simple MPI application. This is the hello world equivalent of MPI. So there's a header file, mpi.h, that provides all your MPI functions. But it just looks like a normal application, and I call some functions. So I've got my MPI init. I ask how many CPUs are involved in this parallel job, because you specify the number of CPUs to run on at runtime. So an application is only hard-coded to a number of CPUs if you do that in your algorithm. Otherwise, you have functions to find out how many CPUs. MPI rank, this is the first time something changes. So if I ran this on 4 CPUs, I have 4 copies of this code running. So the variables, like rank, num, prox, tag, message, I have 4 copies of those, 1 on each CPU, right? When I call rank, the variable rank on all those 4 CPUs now diverge. One's got 0, one's got 1, one's got 2, one's got 3. So very simple workflow here. If my rank is not 0, I call a function called MPI receive. This is the very simple receive data from a single CPU. And what is it? I want to receive one variable, that's an int, from 0 with tag, because these all have to match for the communication to happen, in a communicator called MPI world. If you want more details on a communicator, refer to my slides and ignore my calendar reminder. And there is something called a status object. So there's something interesting. You can send less data than you say you're going to receive. And the status object will actually give you information like how much did I actually receive, who actually sent it. So then when I receive that message, I print out this hello from process rank. So the else, so what would be the else? Else would be CPU 0, right? So CPU 0 is kind of like my master in this case. I print out the number of processors in the parallel job, and then I loop over all the CPUs and I send them the value equal to themselves and finalize. So this is a very convoluted, doesn't really do anything. So if I run this on 4 CPUs, what would I expect to happen? I would see MPI world is 4 processors big, but then I would see hello from process 1, 2, and 3. I would actually see that same printf printed 3 times.
Necessarily see it in order 1, 2, 3?
No, order, when you just call printf, order is not guaranteed. Every time you run it, you can get different results. So I'm actually going to compile this and run it.
So how does it aggregate everything onto one standard output? That's done under the hood for you?
Yeah. So whenever you run an MPI application, you need something called a launcher, and this varies between systems. A very common one is called MPI run. We're going to run this on 4 CPUs. And so this is what I say at runtime that I'm going to run 4. So ignoring these messages saying that it can't find InfiniBand, here's the actual output from the application. MPI world is 4 processors big, hello from 1, 3, 2. So what's happening in the background when you do MPI run, what it's actually doing is it's starting up this extra helper utility, and then that spawns all the other processes, and their standard outs are attached to that helper utility, and it's got the network connection back to the original MPI run. And so that's how that works. But you really can't guarantee order ever. So this introduces a bit of complexity for debugging, right? If you start doing your regular printf in the middle of wherever, you got to also say, okay, who sent it? Do I really want to pay attention to, 3, etc.? So we actually have a tool called DDT, which is a parallel debugger for MPI that aggregates and organizes messages saying where they're coming from. So communicators specify groups of processes. I guess I will go into this because this is important for understanding collectives. There's a default communicator called MPI world, and that represents all the CPUs in the job. You can make new communicators. You can give communicators that have physical meaning. You can create a communicator that's on a Cartesian grid. So CPU 0 is assigned grid 0, 0. And you can the spec supports up to 8 dimensions in that grid, and they can all be, every dimension could be periodic or not periodic. But most people stick to managing that themselves and use just a 0 through n-1. Most people, MPI world is sufficient. Tags are, again, just used for distinguishing between 2 messages. notice when I was sending data, I said an int and I just gave it an array. I no longer have to worry about sending X number of bytes from memory. MPI does all that for you. And you can make derived data types. So say you have a struct that has 2 doubles, a 4-character long character array, and an int. You can send 5 structure things. And you can also specify striding and all these other funny things. So then you can kind of communicate, data structures that have some sort of physical meaning inside your problem rather than having to worry about, I got to pack these things together, make a serialized object, and then send it. The MPI library does all that for you, so you can think in these more higher level terms. So I already showed you the sends and receives in the hello world example. So there's something that can happen in MPI. Notice for every send, there was a matching receive. What happens if 0 tries to send to 1 and 1 tries to send to 0 simultaneously? In MPI, that will block. That will lock up and sit there forever. And it will look like it's running. You'll see 100% CPU use, but it's not actually doing anything. So this is actually a common problem. I have an example of a code that does this, and it does exactly this. Everybody's trying to send to everybody, but nobody's trying to listen. And so the code will sit there and run for forever. It's pretty simple. First, everybody tries to send, and then everybody tries to receive. Since everybody tries to send first, everything locks up. So this looks very clean, but this will actually is what's called an improper MPI application. In some cases, it will run. In some cases, it will not. And that's because of certain types of optimizations certain MPI implementations assume. So how can you handle this? There's actually, for this specific case, there's actually a function called send-receive. So you don't have to have every even process send, every odd process receive, and then swap. So you can keep your code cleaner. This is something to be aware of. Sometimes codes will just stop and look like they're running and not progress. Normally it's because of an error like this. Because of the optimizations that some MPI libraries assume, you'll run into the case of it worked until I went to a bigger problem. And that's because what they do is to try to improve performance, they'll do what's called an eager send. They will send the data to the other CPU before the other CPU asks for it. But when the data gets so large, it can't assume that there's going to be enough free memory on the other side. It'll stop doing this eager send, and it will wait until there's a matching receive and write the data directly to where it's supposed to go. And so that's why when you start small, it'll work, and when you get bigger, it will stop. And so when it stops, that's when you can be like, okay, I've probably got a deadlock somewhere. I need to look at my messaging logic to see whether or not 2 CPs are trying to send to each other at the same time. And that parallel debugger I mentioned earlier, DDT, it actually has something called a message queue, which you can point it at an MPI application that's hung, and it will show who's trying to send to who and who's expecting to receive from whom. And so you can kind of see who's currently hung up. And it saves a ton of debugging effort. So collectives, there's a number of different types of collectives. Collectives, instead of saying 1 send to 2, collective is for groups of CPUs. So this is where that communicator becomes important. You say everybody in communicator comm world receive data from CPU 0. That's a broadcast. Everybody do a reduction. Everybody do a scatter. Everybody do a gather. So this is like what the prototype for broadcast looks like. You have the data you're sending, the number you're sending, the type you're sending, who you're reading the data from originally, and that's the root process, and then the communicator. So here's an interesting thing. What data structure on the receiving CPUs do I write the data into from this broadcast being sent from the root process? That buffer on the root process, that's being read. On all of the non-root processes, that's the one being written. So the names variables don't have to match, but you do have to call broadcast on every CPU in the communicator. because they have to, basically the broadcast on the non-root processes, when you call that, that's the receive, to receive it from the root process. So collectives have to be ran. You can't just run this on the root process and expect everybody to have the data then. Everybody has to call it. So I have an example. It's an integration example, very simple, trivial parallel problem. I'm going to do break a function into rectangles, evaluate it at points, and sum them all together. So I'm going to do a couple of different things here. First, I'm going to broadcast an input value from one CPU to all of them. They're all going to do 1/nth the rectangles, get a local sum, and then I'm going to do a reduce, which is another type of collective that takes the values from all the CPUs, does some operation on it, in this case a sum, and stores the result on a single CPU. So unfortunately, I only have this in Fortran, so it's pretty simple. I start again with my MPI init. I find out which CPU I am. I find out how many CPUs are in the whole run. If I'm CPU 0, I say how many CPUs, and then I ask for an input value, something on standard in. How many rectangles do I want to do? But then notice outside that if block, so if I'm running this on 4 CPUs, all 4 cores execute this broadcast call. So send the value n, which is a number of rectangles. It's only one value. It's a double. And sending it from CPU 0 to all the CPUs so that they can then use that value n to find out how wide a rectangle is. So I had that value on one CPU. After the broadcast, I have it on all of them. They each do a loop, but notice this loop, how I broke up this loop. I iterate, but I step by the number of CPUs. So CPU 0 does, rectangle 0, 4, 8, 12. CPU 1 does 1, 5, 9. 2 does, 2. 2 plus 5, you just keep. So everybody's doing 1/4 of the rectangles, and they're all shifted by the number of CPUs they are. So it's the same code being executed by multiple CPUs, but because of unique values being different, like which CPU they are, they do slightly different calculations. When I'm done on each of the CPUs, now I've got a local sum. I have 1/4 of the integral on each CPU, and so I need to sum them together. So that's where the reduce comes in. So I call reduce on all the CPUs. I'm sending and I'm storing the value in total. I'm sending one value. I'm doing an operation type of sum. There's a number of defined operations that a reduce can do, defined by the MPI standard, but you can write your own, and then you can register them. So you could make a median or a more complicated reduction function, and then just put its name there, and you can now have this nice simplified way of get all the local values and do something to it. And I want all the CPUs, and I want rank 0 to store the sum result. And then if I'm 0, take that result, normalize it, and print out the value. So if I actually run this, MPI F90, and so here's the actual output from the application. So here's an interesting thing about MPI. You should not look to MPI so much for speeding up your application. You should look to MPI and parallel programming for letting you do a bigger problem in the same amount of time. It's a different way of thinking, and it's subtle, but a lot of times, if you're just trying to speed something up infinitely by throwing more CPUs at it, you'll get diminishing returns, and sometimes it will actually go slower because you accumulate more and more latency penalties and stuff for the communication. So a lot of times, keeping the amount of computational work per CPU constant and then doing bigger problems, if that's what you're trying to do, and then scaling out to more CPUs actually gives you the kind of time to solution speed up that you were looking for. So that's an example of a collective. So that's really all I had on MPI. That should be an overhead of kind of how those processes, they can be on any type of machine. It doesn't care what kind of network you're using. You don't have to do system level programming. You can just say send this array of n doubles or broadcast it everywhere else and let us and the creators of the MPI library worry about optimization of how we do a broadcast. Because that broadcast, what's the naive way of doing it? I could just loop over and send to each CPU. First send it to 1, first send it to 2, first send it to 3. In the background, we're actually doing something much more complicated that gives you much better aggregate performance. What we do is we simultaneously send the data to 2 CPUs. So we get half the performance to each, but then those 2 CPUs, they continue the broadcast to 2 more. So we build a tree. So instead of the amount of time to do a broadcast being how long it takes to send to 1 CPU times the number of CPUs you have, ours is log n. Because every time you double the number of CPUs, we only add 1 more step in time. So you don't have to worry about those kinds of optimizations. You just say, I want to get data everywhere, and we do the craziness in the background.
I'm just curious, is it optimized that relative to the network?
For like network geometry?
Yeah.
Not the library we use currently. If you use something like a Cray where they've got the torus networks, they definitely do. Because you want to minimize the hops. Yeah. Machines like the Blue Gene, they actually have a specific network just for broadcast and reduce. You can do some interesting stuff. There's actually quite a bit of research going on in this case because there's very complicated functions. So there's a function, so MPI reduce. You get the result on 1 CPU. There's something called all reduce, which is you get the result and it ends up everywhere. So it's like a reduce followed by a broadcast. But there's actually ways if your function is, was it commutative or associative? I can't remember which. I'd have to work on a paper to prove. But where you can kind of do it in a more intelligent way where you can have data flying all over the place all the time and end up with the same result everywhere. You have more computations going on, but network's normally your slow spot. So you assume that computation is faster in network, so let's utilize more of the network all the time, and we'll spend more on computation. There's a lot of work there. There's also been work done with doing the work in like a switch aggregation point. So instead of doing the reduction operation on the CPU, export the function to the network switch. There's actually a product from Voltaire you can buy that can do this. So instead of having to send stuff to the endpoint, you can kind of send data to the switch. The switch does something, sends it all back to the host.
So is the function fairly simple?
That's one of the problems, yeah. It introduces complexity. So again, that's all I had for MPI. Is there any questions about that? So from here on out, I actually do not have any slides. So now we're going to talk about compilers. I'm going to cover a couple different things. I'm going to cover using an optimizer. So how many of you today compile your own code? How many of you use an optimizer? Oh, 2. Oh, okay. So you're all, what are you doing here? A lot of people actually don't do that. It's very common to see cases where people run applications on an HPC service, let it run for hours and hours on end, and they didn't know that if you turned on a little flag for the compiler, they get a nice little, decent percentage performance improvement. So I'll come back to using an optimizer. So you guys all use C. What if you had a solver that someone else wrote in Fortran? Did you know that you can actually call Fortran from C? You can do this. I've got a demo here. So I have the single precision dot product from the BLAST library reference implementation. This just calculates a dot product, but it's implemented in Fortran. This is actually not a problem. So I'm going to remove a little bit of the covers of what a compiler does. So for compilers, there's a front end and a back end. The front end takes in C, Fortran, C++. The back end kicks out machine code. So there's steps in between. You can get an object file that's filled full of assembly instructions that then you put together. So what you do is you actually take the compiler, and the most common option is -C. And this will kick out a file, s.o. This is an object file. What do object files provide? They're an already compiled version of the source code in the machine language for your machine, but it is not a working executable. It provides symbol names. In this case, s. Notice that underscore. Fortran compilers normally stick on this extra underscore. So let me show you the C code that's going to call this then. I create a prototype for the Fortran function, but I have to give the underscore. But this is actually the C equivalent of the prototype for the Fortran function. Notice everything's a pointer because everything in Fortran is by reference. Everything in Fortran is by reference. So notice everything I'm saying send the pointer of. So in this case, now I've got C code that goes and calls that Fortran function. So let me try to compile this C code like how I would normally compile it. So how many of you have seen this message before? Undefined reference to s. An undefined reference is a function that you're calling that is not defined anywhere in your code. Okay, so that's kind of circular. That means that is provided by something else. Kind of like, so when you get those kinds of messages, that means you need to include code from someplace else that provides that name. So NM is a tool that will tell you on an object file and executable what symbols it provides and requires. So if you see this capital T, that is what it provides. So this s.o from that Fortran provides that. So now if I just do this, and order matters, now I'm golden because the .o provides that name, that function name, s. So this kind of showed two things. It showed mixing C and Fortran, and you can go the other way around. But it also showed this common problem of undefined reference to. When you run into those undefined reference to, what you can start doing is you can start running NM on object files and library files like .a's and .sos. Find which one you need and start sticking it on the end of your link line. And this is an iterative process I go through all the time when I have stuff that I'm trying to build and it says it can't find something. I find what provides it, and I say, okay, here it is. And you can just keep sticking it on. And so then that runs my dot product just fine. There's one other gotcha for mixing C and Fortran, though. When you start, so this was a simple example. It was a one-dimensional arrays because it was a dot product. When you start doing matrices, Fortran and C, the matrices are ordered differently. In Fortran, they're in column major. In C, they're in row major. So what that means is if you pass the matrix in to a Fortran function, you want to pass in the transpose of it. So it's kind of something to watch out for. That's the one gotcha with that. But point is, yeah.
There isn't a problem with the calling sequences. The calling sequences, the parameter order, Fortran and C use the same assumption about which parameter is first in the stack.
Oh, like arguments for a function?
Yeah.
Okay, so question was if the ordering is the same. Yes, pretty much the first one's the first one, the second one's the second one, the third one's the third one. And types match up too. But you're going to run into issues with special types like complex. But there's ways around that too. This was a very simple example. But in the end, if you're looking at a very complex set of code that provides some functionality, figuring out these issues are easier than re-implementing that whole thing in C.
Oh, sure. And as far as the call where you had everything as a pointer,
Yeah.
if you made the mistake and you do that, you're screwed. It's not going to warn you.
No, it will, because watch what happens. Or wait, no. Yeah, you are just screwed.
Okay.
Yeah, because it's going to pass in the wrong value.
It doesn't know that it's Fortran.
I had issues where I had my prototype right, but then I was passing in arrays, not giving them the reference symbol. And so then I just get the normal type mismatch in the C preprocessor because the prototype doesn't match what I was calling. But that wouldn't solve the problem you're asking about. Yeah. No, you run into it. I mean, there's still some stuff you got to watch out for. That's why a lot of times there's certain libraries out there that provide either Fortran bindings or C bindings, and they provide either interfaces or header files already for you, even though the back-end implementation of the actual code that's already been compiled normally is in Fortran or C, or it doesn't matter, as long as they provide a header. So like a good example of this is the FFTW library, fastest Fourier transforms in the West. It's a FFT library from MIT. It's implemented in C, sort of, but it's C for the most part, and they have a Fortran interface where they've already got Fortran prototypes and interfaces for calling the C functions. So this is something to be aware of, that yes, you can mix these things. So if you're out there and you're like, oh man, I've got existing code base, someone's already done what I want, languages don't match, not a problem. And it can get really complicated too. You can call C from Python, because Python itself is actually written in C. And you can start mixing those kinds of things together. It's becoming more and more common to see scientific applications look like a Python application, because Python gives you all these nice string manipulation and file parsing and high-level capability, but the performance is low. But then you implement a Python bridge into a Fortran or a C solver for your heavy lifting, where you spend most of your computation time. So you have a solver written in C or Fortran, but then your front-end input and output parsing is all done in Python. And there's actually native ways of doing that in Python. That's what a Python module import normally is written in C or some other language. Not always, but a lot of times. Any questions about mixed language linking? Okay, so optimizations. I just want to make an example of how good optimizations really can be. So I have a code called stream. It's actually a traditional benchmark. And it does three things over and over and times it. It copies one array to another. It copies an array and adds a value to it. Or it multiplies two values of an array and adds a third value and stores the result. So it's very simple, very tight loops, very straightforward. If I run this with debugging symbols, because I see people do this all the time, so this is with no optimizations. We wait. And so this is a very, very simple code. Conceptually, this should be, I mean, a human could write the assembly for this very easily to get maximum performance. But compilers are procedural. They can't actually do that very well. Compilers, for the most part, when that front end runs and parses out your Fortran into an intermediate language that the assembler then uses to create assembly out of, normally that code has zero performance assumptions injected into it. This is where the optimizers provided by the compiler stick in between. So I've got this average timing of 0.38 seconds for copying. Now if I disable this and go with just regular capital O2, notice all these extra messages the compiler kicked out. Loop was vectorized. Vector units, otherwise known as SSE or AVX instructions, are really high-performance ways for doing the same operation, large collections of numbers simultaneously in a single clock cycle. And so this is kind of parallelism internal to a single core. And so this is just a little bit faster. We get like 20% or something like that. Where's my mouse? Yeah. And then here's something else. Unfortunately, this example is too small to actually have this work, but there is a flag for the Intel compiler -parallel. This is an automatic parallelization. Now, this is not MPI parallel. This is shared memory parallel. This is going to try to find loops that it thinks it can do independently of each other. There's a lot of restrictions on this. It's a lot better to, if you're going to want to do this, to do your own explicit parallelism. But this will automatically try to use all the active cores on the machine. But in this example, it does not actually speed this up at all, because this is actually a memory bandwidth bound problem. It's not a computationally bound problem. So I'm already maxing out the memory bandwidth internal to the machine. But that's something you can always try. If you've got an existing code base, why not? It actually slows it down. Don't just throw stuff on without testing it. Things can get worse. But you can throw that option on, do a test, see how it does. Computer resources versus development time. It's your choice where you want to spend your available resources. So, moral is, always use at least a basic optimizer. Capital O2 is a common, easy one to use. It's generally pretty safe. If you start getting more aggressive with the optimizer flags, O3, X-host, you're going to run into issues where precision starts getting relaxed. And so some applications, that's fine. For others, you'll get wrong results. So you need to verify your results when you start getting aggressive with the optimizer that it's actually giving you what you'd expect.
Precision in terms of numeric precision?
Yeah, so example, X-host enables the ability of greater vector instructions. Vector instructions are all done at 64-bit precision. Now you may say, like, well, things have always been 64-bit. Not true. Floating point precision in a normal floating point unit is actually 80-bit and is truncated to 64 when it's written to memory. So you have extra precision when you're doing your actual math on the CPU. It's actually 80-bit, not 64. But when the compiler starts sticking out vector instructions, you only have 64-bit. And so you lose a little bit of precision on the end. So if you're sensitive to that, you will run into issues and you will get bad results. That's just one of many examples.
What about O3?
It's relatively safe, but I have seen things go bad.
What does it do that would be unsafe?
That varies compiler to compiler. There's so many different heuristics these things look at. So when you do something like O3, that's a bundle of things the compiler is going to start doing. What it does, nobody knows. You can go, most of the compilers support the ability where you can start putting these special comments in your source code. So you can say, this function do not do vectorization. If you have one function that's sensitive to it, so you can compile your code on the command line using a given option. So everything has that optimization applied to it, except for that subroutine or function that you put that special comment on, or that special line, or there's different ways of controlling it. So you can get very, very fine grained. It's not commonly used, but some people, if they're going to run a lot of stuff on the same code, they invest that effort into it. Before you want to start getting that level of detail, though, you want to investigate something called a profiler. I'm not demonstrating a profiler, but a common profiler that's available for serial code is called gprof. The Intel compiler suite provides a couple of other ones that are quite nice also. Even tools like MATLAB for themselves have a profiler. What a profiler does is you run your application for real, but it instruments it. It slows it way down, but it times every line and function call. So you can look and drill into your application and find where your time's being spent. And then you can focus on those parts of your application for performance improvements. So if you're going to invest into like shared memory parallelism, you can do that incrementally. You can find out where you're spending most of the time in your code. And the surprising thing is, most of you are probably thinking, well, I know where I spend the time in my code. And that's probably true 50% of the time.
I would say less.
It's very common for people like, oh, well, I do this, and it's computationally expensive. But computers are weird beasts, and they have memory hierarchies and other stuff, and you will find that the thing that is actually slow is not always what you thought it was. It's not always the thing with the most additions and subtractions and multiplications. So I want to show you a common trick I use. There's a debugger called GDB. It's a commonly available free debugger. And I use it all the time to solve a very common problem, otherwise known as a seg fault. So signal 11 or segmentation fault is a common problem because you stepped outside of array bounds and other such things. So I have a simple code called seg1, and all it does is call function1. Someone's going to yell at me for my very hastily put together contrived example. And function1 calls function2 from this other source file. So I'm going to compile this. Oh, I never added to the make file. So it compiles fine. All the types match. Oh gosh darn it, don't do that. You don't always see them too, but this code is technically broken. So I get this seg fault. It's funny, because when I'm actually trying to program stuff, I get seg faults all the time I have to go and fix, and then when I actually try to create one, it wouldn't let me. So you get a seg fault. What can you do? You can compile with -g. This adds on most compilers called debugging symbols. This includes like the source code and other information so a debugger can attach to your application and give you certain pieces of information. There's lots of stuff you can do with a debugger. You can step a code line by line, look at variable values. You can even now in the newest versions of GDB work a code backwards where it stores state of variables over time so you can step backwards in an application. So you run GDB and you give it your application. It kicks out some stuff. But then you just type run. And so this actually runs the application. And so it got a seg fault. And it actually tells me the seg fault is in function2 and source file function1.c on line 10. So it already told me where that seg fault actually is, so I know where to start investigating. But there's something else. Notice that function2 was called by function1, which was called by the main program. I can find that by typing where. Function2 got called by function1 from function1.c on line 14. So you run it, you type where, and it shows you what's called the stack. An application is done when the stack is done. The stack is just a list of what functions you're in currently. This is a very simple way of thinking about it. So you have your main application, which is called main. Even for Fortran, it's called main. You call a function. That function gets added to the stack. In that case, my first function I called was function1. It called another function, function2. That got added to the stack. And so when function2 is done, it gets removed from the stack and I go back to function1. When it's done, it gets removed from the stack and I go back to main. When I'm back at main and it exits, I'm back to the operating system, so my application is done. So one way to think about applications is that they're actually a function being called by the operating system. So this stack, when you have these seg faults and you get the results and you run through GDB and you type where and you see this stack, if you're calling a function from different places in your code, because normally the errors I get from seg faults don't come from the function itself, it's the values being passed into that function because I have bad error checking. And so I don't want to know the function where the problem was. I want to know what function called it. So I can go look there, maybe rerun the debugger, put a breakpoint at that function, and look at the values that were passed into it. And you can do all that without having to modify your code and add printfs. You can do it all here, and you can just print out variable values. So debuggers are very powerful tools. GDB works great. It exists on pretty much all systems because it's free and widely available. For MPI applications, this gets convoluted because when I run on 4 CPUs, I have 4 things running. Which one is GDB actually talking to? And so that's where things like our parallel debugger, which I have time, I'll demonstrate, come into play. Okay, so I want to show you guys a makefile. Does anybody here use makefiles right now? How many people here know what a makefile is? Okay, because a lot of people just get them given to them. So I'm going to do a quick refresher of a very simple makefile. So make is a build system. but it is not tied to code specifically. You can have it do anything. Like example, make clean. I just had it run rm just to delete a bunch of files for me. It can run arbitrary commands. So what's a make file look like? It's just a text file called makefile. They can have different names, but if you want to be able to run make without specifying a name, it's got to be called makefile. And you have a target and a dependency. So in this case, I have a target called deadlock. The dependency is deadlock.c. And I've used some variables here, so let me scroll up. So I've got a variable MPI cc for specifying which compiler to use. So all this makefile is going to do, when I type make deadlock, it sees that it's got to take deadlock.c, and it's going to fill in these values. So it's going to say MPI cc minus 202 x host, because that's the C flags. It's going to throw in this preprocessor thing, which has to do with that code specifically. And the output file name, this $@ gets filled in with the target name. You can type in values here, but this is just shortcuts. And the $? is the dependency name. So let me actually do this. If I do make, so you notice this looks a lot like that line in that make file that I did. But check this out. I'm going to run it again. Up to date. Make does something else. If the target, which is the executable deadlock, is newer on the file system than the source file, the dependency, which is deadlock.c, it does not recompile it. So let's look at another example. Dot product. So dot product depends on s.o and c.o. So this is a more complicated application. Remember, it's got two source files. I've got to compile one with a Fortran compiler and one with a C compiler. So you can see having a more complicated application where you've got many source files. And so you can have a target for every source file, and now this is all you have to do. It figures out the dependency graph for you. Because dot product depends on .o, c.o and s.o, notice I have down here the targets and dependencies for s.o and c.o. So that means that when I say make dot product, it's first got to make s.o and c.o. Come on, Flux. Watch very closely what happens here. See, it ran 3 compiler commands for me. So what this does is when you start having complicated code with lots of source files, you don't have to type these things out over and over. It builds it for you. So at first it ran the Fortran compiler to get s.o, then it ran the C compiler to get c.o, and then it linked them all together with the C compiler to get the resulting executable. So what's this also mean? Creating s.o and c.o do not depend on each other. I could, in theory, compile both of those at the same time. So watch this. Make minus j tells make to spawn parallel builds simultaneously. So if you've got a code that takes like 15 minutes to build, if you get all the dependencies set up right, you can say like use 4 cores. It actually compiled both s.o and c.o simultaneously. So this is a very short example, but on the other hand, is anybody here familiar with OpenFOAM? OpenFOAM takes a very long time to build. I normally build it on 16 CPUs and it still takes me like a half hour. If I didn't have 16 CPUs in parallel make, I'd be waiting a heck of a lot longer because it would compile one at a time, letting all the CPUs sit there. So you can have this do parallel things. Here's the thing though, make, while it's generally used for software builds, you can use it for other things. So check out this. Notice down here, hello, that's an M file. Where's my mouse so I can highlight it? This is MATLAB. I'm going to use the MATLAB compiler and compile code. Make doesn't care. Oop. It doesn't care what command it runs. So I've seen people use make to spawn their actual simulations. So make's just a handy tool so you can control stuff in simple ways. It can handle all the dependencies for you. So all you have to do is like, okay, this source file depends on these ones. So like Fortran, this is really handy because in Fortran 90 where you have Fortran modules and you got to create the modules first before things that use those modules, you just say that the ones that use them depend on the ones that provide them. And so you can say make minus J12 because a Flux node has 12 cores, including the login nodes. It'll compile all the ones it can first and keep moving down the line until it gets the thing you want. So let's go back and look at something else. Remember how it checks to make sure that the application has actually changed? What if I wanted to change just part of C dot? Say I wanted to change this value to 4. Okay, so now C dot is newer than C dot.o. Watch what happens. It did not recompile the Fortran code that was not touched because the object file is still good, so it reused the existing object file. So if you have a large code that takes a long time to compile, you can modify just pieces of it, rerun make, and it only recompiles what's changed. And so it can save you hours of waiting for compiles. So that's why I encourage people to use make. Any questions about that? So the next thing, I want to give you guys a couple of pieces of information you can look up yourself. The next thing you would look to after make is what it's called a revision control system or a software control system. People call it different things. The most popular ones I'm aware of are Git, G-I-T, and Subversion, otherwise known as SVN. Can't recommend these things enough. How many people have ended up with code.c, code v2.c, code v2 fix.c, that kind of problem? This solves that because a revision control system keeps track of all the changes you've made. And so you can go to the revision control system and say, hey, what did I change in the last two times I modified this code? And it will tell you. You can get changes from other people you're collaborating with and import their changes and maybe kick out their changes if you find it breaks something because you can step backwards in time. But you no longer have to have multiple copies of your code. In fact, this MPI presentation is held in a Git revision system that you can get access to. It sits on the UMich website, and you can actually download this code and see every change I've ever made to this slide deck. So anytime I change something, I put in a revision system so I can find out what I did in a previous time. They also let you do neat things called branching. If you want to test something, you can make a branch, which is it changes all the code in your repository. So when you first make a branch, nothing changes. You make it from some branch in your timeline. And then you make changes, and if you decide, hey, something that didn't really work out, you can delete that whole branch, end up back where you started. And you can switch back and forth between those branches, so you can have a working version of your code and a development version, and when you've implemented that new feature, you can do what's called a merge and bring them back together so that you don't have to manually figure out what did I change and what didn't I change. So I highly recommend checking that stuff out because it'll save you so many headaches of which is the right code to use, which version is it, what did I do, what did I change that caused something to break because I discovered the break 6 months after I probably created the break. These kinds of things happen all the time. So, yeah.
So you have a preference for between SVN and Git?
I personally use Git because that's what I learned first. Also, I like the way I use Git very heavily without an actual Git server. And I like the way Git works where it's no single point of authority. So my laptop's an authority, Flux is an authority, my IFS base is authority, it doesn't matter. There's no checking out and locking of files so that if I'm modifying one, someone else can't modify a different one if you're working with multiple people. So that's why I like Git. And Git's really, really fast. If you've got a huge code base, because Git's designed around a Linux kernel, it's really, really fast. But that said, if your collaborators are already working with something else, using a tool that you all understand and learning curves, most of the time, use what you know. Any other questions? So we got about 10 minutes left. I'm going to demo the parallel debugger. So to use this, you have to have exporting because it's actually a graphical application. I'm not going to cover what that is, but if you want to know, you can talk to me afterwards. So what the parallel debugger, otherwise known as DDT, does is it spawns all your parallel processes and attaches GDB to every single one of them, but then it returns results and aggregates them to you in a very understandable way. I actually use DDT a lot, even for serial codes, just because it provides me a nice interface. No, it's not. So I've got or wait, don't I have the yeah, there we go. So this is the deadlock code. If I run this on 4 cores, it will sit here and hang for a long period of time because this is that one that they're all trying to send to themselves simultaneously. It'll sit here forever. So what I want to do is I want to recompile it using debugging. So how I'll do that actually is I'll just modify my makefile to enable debugging symbols. And I'm going to run DDT deadlock. So because of exporting, I'm actually going to see the graphical application show up on my laptop here, but this is actually running on the login node on the cluster right now. For intensive applications, don't actually run this on the login node. There is a way to run this through the whole PBS batch system onto the cluster. So, because we can debug up to 64 cores at a single time. I'm going to say run and debug a program. There's a bunch of other capability. Like this isn't a GPU code, so I'm not using CUDA debugging. And what kind, and I'm not doing any type of memory debugging.
But
So,
it does support CUDA.
yeah. So it's actually spawning the 4 CPUs, and it's going to pause it. So I actually see my source code here. So I've got 4 CPUs here, and if I actually hover over this line, see it says on this line, all the CPUs right now are on the same piece of code. So I can actually, with DDT, step one line at a time, a single CPU at a time, or a group of CPUs. Or I can pause an application and find which CPUs where. For every variable, depending which CPU I currently have selected, the variable values over here will change. And here's that stack also I mentioned earlier. So you can look at the variable values across everything. And actually, it has functionality. So let me, do I have a variable that would be good for that? Yeah, let me put a breakpoint here. So the code's going to run to that point and stop. Okay, so all the codes are here. So check this out. View, cross-process comparison. And I want to look at the variable rank. The variable rank on processes 0 through 3 has different values on all of them. So this very quickly lets me look at variable, and you can do complex, you can do array and array subsets and multi-dimensional stuff. And you can actually see values and compare them across CPUs. And this actually works for shared memory program also. That has a cross-thread comparison. So I'm going to keep running this code at this point, and now it's just going to hang and hang and hang and hang and hang. So I'm going to pause it and see where everything is. Notice they're all on MPI send because they're all trying to send. Stack, main, then they tried to send, and then these are functions inside the MPI library they're currently trying to do. So let's look at another thing. Message queues. In MPI com world, right now everybody's 0's trying to send to 1, 1's trying to send to 2, and they're all trying to move 8,000 bytes of data. Why? Because I'm moving 1,000 doubles of 8 bytes each. So it can actually show me who's trying to send to who. So this is a very simple graph, of course, but this could be up to 64 with complex things of different CPUs going different places. And you can do the same thing for receives, which I'm not trying to do any receives right now. So the debugger can actually show you who's trying to communicate with who. And you can get information, except pointers, they're pointers. They'll give you information like what's your current tag value, how long it is, and what it's trying to do. So you can get a lot of information. I didn't have to add a lot of instrumentation to my code. Actually, I didn't have to modify the code at all, and I can get a lot of information out of it. So that's everything I had. Any other questions or interest in demoing? Yeah?
Is there a parallel profiler?
There is a parallel profiler. So the parallel profiler is called opt, and is made by the same guys. The parallel profiler is interesting because it focuses more on timing the communication between the CPUs than the actual computation on each CPU. But it does do that. But it's neat. It actually gives you a timeline. Let me start it up and see if I have anything set up right now, just so you can see. The parallel profiler comes in 2 different pieces. There's a library that you link your code against, and you run it. And it stores in a database all the communications and information that happened while it ran. And then you have this thing called opt GUI that you can then look at the results of that run, and it actually lets you compare 2 runs to each other. So I used to have, I'm hoping I still have it on here, but the database might be down right now because we were doing some maintenance on it. A comparison of a code ran on InfiniBand and then with InfiniBand disabled. And so it's the exact same application on the same number of CPUs, doing the same mathematics on the same CPU type. The difference was the network used for communication. And so then you could actually see how much the network type affected the performance of the application. And I believe in that case it was actually pretty significant. And we'll see if we get any results here. Waiting for a license, that's not a good sign. It might still be down. But yes, there is a parallel profiler. There are free versions of parallel profilers. There's one called Jump Shot, and there's another one called Tau. Tau is the more comprehensive one.
If you use those fields, that wouldn't require installing any software on those.
No, because normally they're just a library that instruments an existing MPI library. Is it going to connect or not? The profiler doesn't get used very often. The debugger gets heavily used, but the profiler not so much.
Can I ask you about the different compilers? Because I noticed you were
Yeah.
using Intel components.
Yeah, I was using that just because they're our default.
Okay, is that generally preferable to GCC?
Normally, the Intel compilers get functionality for new CPU features on Intel CPUs before GCC gets them and stuff. But if you want stuff to be really portable and accessible to people, make sure it works with GCC.
But in terms of if you have a choice,
I always use Intel if I have the choice, personally. And then actually after that, I tried the PGI compilers, and then I use GCC. When it comes to C++ code, that's a different story, and a lot of times G++ is just as fast. C++ introduced a lot of constraints that really makes optimizing code difficult, and there's been so much focus on that in the GNU stuff that they're as good or better than a lot of the commercial compilers. And the commercial guys are so focused on scientific codes that are pretty much Fortran. Fortran gets a lot of focus. C for performance, that C++ is kind of second fiddle. There's a lot of people would argue with me on that, but that's kind of been my view of what's been happening.
I ran some tests.
Yeah, what was the result for your application?
Deal. Yeah, well, I had, out of a large set of runs from the parameter sweep, I chose 5 that would be spaced to
Uh-huh.
the runtime from slowest runtime to fastest. And the Intel compiler was generally faster, but it was significantly slower on the 4th slowest run. So, I guess it's just.
The ultimate sysadmin cop-out, it depends on your application.
Oh, yeah, of course. Yeah.
So, any other questions? Okay, it did connect, but I don't have any runs on here currently. So I could, do we have like a break right now, or what do we have?
Yeah.
We do? If you want, I can whip together, I can just do an example real quick.
If nobody else is interested in something.
Okay.
Thanks.
Yep. But yeah, so when you've ran some profiler runs, they would show up here, and you can select them and view results. I really wish I had one, so gosh darn it, I'm gonna make one. Yeah, it's gonna be a convoluted example, but let's do the.
Catastrophic error, not just a plain error.
You're gonna see how I work here a lot. Oh yeah. Has to do with some weird thing in the Intel compiler dealing with dynamic libraries. I had looked it up once. I don't remember exactly what it is.
Because I just started seeing it recently. That I've run before.
Yeah, you should always see it. So notice how there's a pause here after the application is kind of done. So the way the opt library works, because notice I had a link in this opt library, and I had to use a different MPI header file. What's happening is it's making a shim function so that the opt version of MPI send and all the MPI calls are being called instead. And so that includes a little extra code, and then it calls the real MPI library in the back end to actually do the communication. So it can start and end a timer, find out what source line it's on and stuff. So now, if I go back to the opt GUI, see, now I've got this run. It was on 4 processors and executable, and it took 10 seconds. So if I view this, I get something that looks like this. Now this is a really bad example. So I get a timeline, every CPU, and how much time on that timeline was spent on different types of information. Why was the broadcast here so long, and on the first one it basically didn't happen? It's because the first CPU asks for input, and so it's waiting for that input before it gets to its own broadcast, but all the other CPUs are already there. So that's why they're all on broadcast. But then here there's some computation, and then there should be something at the end, but because it's our collectives don't show up. Or not all collectives show up. If you have lots of sends and receives, you can actually click this and it'll actually draw arrows between all the sends and receives, so you can see which send was actually going to which receive. And you can zoom in. Oh, there's our reduction. So this is kind of what you get a look at. And it's neat because on a real application, you'll see periodic behavior. Because a lot of things are like iterative, right? You do computation, you have some sort of communication pattern. And then you have computation, you have some sort of communication pattern. So you'll see periodic behavior. The library has the ability to, say, start profiling at this line of code and end at this line of code. There's just a function, 2 functions, a start profiling and end profiling that you can put in your code. So you don't have to, because there's an overhead, and the more functions you have to log, the longer it takes. You can get other sorts of information, things like this. So like compare communication and computation time. And you get the normal kind of profiler. So of the total amount of time spent on stuff, most of it was sent inside that broadcast. And so I can actually get flowcharts of time, and I have different ways of filtering between them. So it can be cumulative or just for themselves, because cumulative all the way to the top, it's going to be 100%, so it's going to be the reddest.
Can you export this information to like plots or text files that you get?
You can save an image of the. It saves an image of it. So yeah, I mean you kind of can. I wish they had more export for just like raw numbers, but yeah, they don't right now. You can get bar charts, line graphs, pie charts. You can compare, different types of communication to each other, and on different metrics. And then if you have multiple runs, like InfiniBand versus not, you can get a different view on the first page where I selected. You can pick two. This will gray out and there'll be a compare, and you get different types of charts. But then instead of having one bar chart for computation time, you have two, and you can compare them to each other. So you can run the same thing twice, or different flags and get different times. Any other questions? Okay, I think we're done. You can find me if you have a question and when you try to use this stuff, if you have any trouble. A lot of it's documented on our website, but if you have any questions, just send it in to flux-support@umich.edu and we'll help you out.